Hello everyone, I am Dr. Atasi, Assistant Professor of Physics, Department of Humanities and Science, MLR Institute of Technology, Hyderabad. So today I will discuss about PN junction, which is in our third unit of Applied Physics syllabus. So here in last class I have discussed about different type of semiconductors, in which I have discussed about P-type and N-type semiconductors. So today we will discuss about PN junction, which is nothing but when we are adding a P-type semiconductor to a N-type semiconductors. So today I will go through introduction to PN junction, then diffusion across the junction, then formation of depletion layer, then IV characteristics of PN junction. So let's go to the introduction. That means what is PN junction? So when two pieces of P-type material and N-type material are joined together using special techniques such as ground junction, diffuse junction method or alloy junction method, that time we get a PN junction. So here in this diagram we can see we are having a P-type semiconductor and here we are having a N-type semiconductor. As we have discussed earlier, so in P-type semiconductor we will have holes as the majority charge carriers, and in N-type semiconductor we are having electrons as the majority charge carriers. So this diagram, this is the schematic representation of PN junction. So here this side shows us the P side and this is the N side. So this is the representation of PN junction. So we can also represent like this, where one side we can show the P-type, one side we can show the N-type. So here this is the schematic representation of the PN junction. So what happens? So when we are joining a P-type semiconductor to a N-type semiconductor, that time one depletion layer is formed. So how that depletion layer is formed? Let us see the formation of depletion layer. So what happens? So electrons from N region will move across the junction to recombine with the holes of the P region. So as I told, here in PN junction we are having one P-type semiconductor to which we are connecting with another N-type semiconductor. So as I have told, in P-type semiconductor we are having holes as the majority charge carriers, and in N-type semiconductor we are having electrons are the majority charge carriers. So what happens? Now when we are connecting a P-type semiconductor to a N-type semiconductor, so these holes from P side will be attracted towards the electrons in N side. So what will happen when excess of holes are going from P side to N side? So a little bit of negative charge will be developed at the junction. Similarly, when the electrons from N side will be attracted towards the holes in P side, that time a little bit positive charge will be developed at the junction. So due to the diffusion of electrons from N region to P region and the diffusion of holes from P region to N region, so two layer of charge carriers will be deposited at the junction. So at P side we will get negatively charged deposited, and in N side positively charged particles will be deposited. So in P side completely accommodation of negative charges will be there, and in N side the positive charge will be assembled. So now we can see in this junction we are getting one side negative charge and one side positive charge. So it can behave like a potential barrier. Now the presence of the charged ions across the junction will stop further diffusion of any charge carrier across the junction. So now as I told, this depletion layer, this layer is known as the depletion layer. This is known as the depletion layer. depletion layer. So this layer will stop the further diffusion of charge carriers to the other side of the junction. Then this thin layer is known as what? This is known as the depletion layer. Now, due to this depletion layer, some potential difference will be established across the junction. So that potential is known as the barrier potential. So due to this depletion layer, some barrier potential will be developed. So barrier potential will be developed across the junction. The potential difference established across the PN junction that is able to restrict the further movement of the charge carriers across the junction is known as the potential barrier or built-in potential, as I have discussed just now. For silicon, this built-in potential is 0.7 volt, and for germanium, this built-in potential is 0.3 volt. This is in this diagram also we can see here left side we have considered the N region and in P side we have considered the P region. So as I have discussed earlier, so here in P side near the junction we are getting negative charges and at N side we are getting positive charges. Due to this, one potential will be developed across the junction. Due to that potential, some electric field will be developed and which stops the further flow of any charge carriers through the junction. So this is the band diagram, energy band diagram of this PN junction. So here the upper side layer is the conduction band and the lower band is the valence band, and in between that we can see the Fermi level. This is our Fermi energy level. This is the conduction band, conduction layer. This is the valence energy level, and this will be our Fermi energy level. So this is our energy band diagram where the upper side energy level is our conduction energy and lower energy is our valence energy band, and in between we are having the Fermi energy level. So as I have discussed in the previous lecture, in P side the Fermi energy will be near to the valence band and in N side the Fermi energy level will be near to the conduction band. So as we have discussed in this diagram that when we are getting this PN junction, that time electrons will be diffused from N side to P side and holes will be diffused from P side to N side. Now, as I have told, there will be some electric field developed due to this potential barrier. So due to that electric field, what will happen? It will push the electrons from this P side to N side, because in P side we are having electrons also. In P side we are also having electrons which are the minority charge carriers. So those minority charge carriers will be pushed from P region to N region by the electric field which is developed by the potential barrier. So that is the drift of the electron. So there will be two types of currents. One is diffusion current, another is drift current. Drift current will be due to the potential barrier. And here in this diagram we can see this is the depletion layer. Now we will see about the IV characteristics of PN junction. So in IV characteristics we need to connect the PN junction with some external source. So there are three kind of biasing. First one is unbiased PN junction. In unbiased PN junction, from the name itself, it is clear that we are not giving any bias. So here this PN junction is not connected to any voltage source. So this is the unbiased condition. So as I have discussed about the depletion region, what the depletion region does in a PN junction. So as I told, it will develop some potential difference. So it will develop some potential difference which is known as barrier potential. So due to that barrier potential, these charge carriers cannot cross the junction. So it cannot cross the junction. From N type to P side, also from P side to N side, these holes also cannot get diffused. That's why there will be no flow of current. So in unbiased condition, there will be no current through the junction. So this is all about unbiased condition. Next we will discuss about forward bias. So what is forward bias? So in forward bias, we are connecting the P terminal of this PN junction to the positive terminal of the battery. Here the positive terminal of the battery is connected to P side and negative terminal of the battery is connected to N side. Positive terminal of the battery is connected to P side of the PN junction and negative terminal of the battery is connected to N side of the PN junction. So what happens here? So when we are giving forward bias to the PN junction, that time it will facilitate the movement of majority charge carriers across the junction. So as I told, in P-type semiconductor, holes are the majority charge carriers and N-type semiconductors, electrons are the majority charge carriers. So when these majority charge carriers will be going through the junction, that time it will result in reducing the width of the potential barrier. So when this condition will be happening? So when the external applied voltage will exceeds the built-in potential, that time only this depletion layer will be reduced, because this depletion layer was stopping the flow of charge carriers through the junction. So when we are giving some external voltage to this PN junction, that time when this applied voltage is greater than the barrier potential, this applied voltage is greater than barrier potential, our applied voltage is greater than barrier potential, that time this width of the depletion layer will be reduced as this, because of the flow of the majority charge carriers. At this time, even for small increase in applied voltage, a large increase in current will be observed. We can see in this figure. So here in x-axis, we have taken the forward voltage and here the forward current along y-axis. So we can see in the initial portion, so as we are increasing the voltage, the current is almost 0. So at a particular point, as we are increasing the voltage, the current also started increasing rapidly. So here this diagram is for germanium diode. So as I have told, for germanium diode, our built-in potential is 0.3 volt. So the current will rapidly increase after we are giving the applied voltage as 0.3 volts. Then we will discuss about reverse bias. So what is reverse bias? So when the positive terminal of the battery is connected to N-type semiconductor, positive terminal of the battery is connected to N-type semiconductor and negative terminal of the battery is connected to P-type semiconductor, that time this condition is known as what? Reverse bias. So we are connecting reversely this PN junction with the external power supply or external battery. Under this bias, current is constituted due to the minority charge carrier. In forward bias, the current was due to the majority charge carriers, but here this is due to the minority charge carriers. We will see how. Here, this reverse bias increase the width of the depletion region across the junction. The excess of holes in P region are attracted towards the negative terminal of the battery. So here we are giving some external power supply, right? So here P type is connected to the negative terminal of the battery, as opposite charges will attract each other. So these positive charge carriers, which are the majority charge carrier of P-type semiconductor, it will be attracted to the negative terminal of this battery. So what will happen? As positive charges will be moving away from the P side, so excess of negative charges will be accumulated in the junction. Similarly, this from the N-type semiconductor, we are having electrons as the majority charge carrier. So these electrons will be attracted towards the positive terminal of the battery. Now they will leave excess of positive charges near the junction. So in this procedure, excess of positive charges will be accumulated in N side near the junction, and excess of negatively charged carriers will be accumulated at the P type of the junction. So now the width of the depletion region will be increased. So as the width of the depletion region is increased, it should be decreasing the flow of current. That means the potential barrier will be more strength, or the potential barrier will be more strong. So at the same time, what will happen? The free electrons in N region will be attracted by the positive terminal, as I have discussed, so that this depletion layer will be wider. So in this reverse bias junction, potential barriers will be more strong and junctions will offer high resistance to the current flow. But very small current will be flowing through the junction due to the minority charge carriers, because here outside also, as I told, these charge carriers will be attracted to the terminals of the batteries. So a very small flow of current can be observed here. So now we will discuss about breakdown voltage. So in this diagram, when I am taking the voltage versus current diagram in reverse bias condition, we can see here, as I told, there will be very less amount of current flowing through the junction. So the reverse current is very less when I am giving some reverse voltage. But what happens when we are keeping an increasing voltage of this reverse bias? That time at a particular voltage there will be sudden change in the current. That means current will be increasing suddenly. Here in this region you can see current is increasing very rapidly. That means this reverse current, that's why I am showing it in the third quadrant. Okay. So now that particular voltage for which this reverse current will start increasing suddenly is known as breakdown voltage. So this is known as breakdown voltage. So this is all about the total complete characteristics of PN junction. In this figure, I have shown both the forward bias characteristics, also the reverse characteristics. So this first quadrant is representing the forward characteristics, and in third quadrants the curve represents the reverse bias characteristics. So in forward bias characteristics, the value of the voltage where the current will start rising suddenly, that is known as the knee voltage. So this point, this is known as the knee voltage. And here in reverse bias, the reverse voltage for which again current will start increasing, the reverse current will increase rapidly, is known as the breakdown voltage. So this is all about the characteristics of PN junction. So summary of this lecture is, first we have discussed about the PN junction. Then we have discussed about the formation of depletion layer. Formation of depletion layer. Then we have studied about the characteristics of PN junction. Characteristics of PN junction, in which I have discussed about the forward bias and the reverse bias. Also I have discussed about the unbiased condition where there is no flow of current. So here from this portion we can get the question like, discuss the formation of PN junction or what is a PN junction, and then discuss about the formation of depletion layer, and with mid diagram show the VI characteristics of PN junction. So if I think this lecture will be very much helpful to you people to prepare with this topic. So this is all about today's lecture. Thank you.